If you're starting to understand a little bit about graphs and some of these ways that we've looked at to find relationships and connections in them, then that's a great place to be in for us to build into talking about spanning trees, and in particular, minimum spanning trees. So the problem that we approach with minimum spanning trees is we're given an input that's an undirected graph where the edges are weighted somehow, or in other words, the edges have a cost or a distance or some value associated with them that might make one edge better than another for us if we're trying to maximize or minimize. In the framing we'll use here, we're trying to minimize the cost or the distance or those sorts of things. And that graph will be in the same form we're used to. It's a set of vertices and a set of edges that connect some of those vertices. The output will be a subgraph of G that is essentially a tree, meaning it's acyclic, and it's spanning all the vertices. It includes all of the vertices from the original graph. Now we call it a tree, but it won't always be obvious from the visuals where the root is. The root will sort of be something that we could kind of randomly select in there because these are undirected graphs. So we're using the word tree loosely here. And a minimum spanning tree is one that has the lowest sum of weights versus other possible spanning trees. There can be multiple minimal spanning trees for a given graph. There are certainly many spanning trees for most graphs. So we take the graph here that's fully connected. Every node connects to every other node. There are many spanning trees for it. We can go around the outside in multiple different ways. We can cross through the inside in multiple different ways. And there are plenty of other shapes that we can make that would get us all of the nodes, all of the vertices from that graph with only some of the connections, some of the edges, and these are spanning trees. They have no cycles in them, and we could pick various nodes in them to be a root and treat them as a tree. In this graph, with the numbers being weights or costs of those edges, there is only one minimum spanning tree. Again, there are many spanning trees, just like we saw previously, but once we associate the costs or the weights, there's only one minimum spanning tree, and that is the one that takes the edges with values 1, 2, and 3 here. To find minimum spanning trees, we'll use two different algorithms. The first one that we'll look at is called Prim's algorithm. They both will use priority queues, or min heaps as we also know them, to try to make decisions about what to pick when trying to build these spanning trees, these minimum spanning trees. Prim's algorithm allows us to start with an arbitrary vertex that we'll call R and treat it as the root of our spanning tree that we're building. We set up a table that has the following columns to it. V, a starting vertex. Each vertex has a row in our table, and then we'll sort of use each of those as a reference in terms of connections to other vertices. Whether this vertex is known yet, whether we have already found its location in our spanning tree, and we'll see how we get to the point of having known something. It's not just having seen it once, but it requires a little more than that. And then D sub V, the minimum distance to V from a known vertex. And P sub V, the parent vertex that is on the path that has that minimum distance, D sub V, the parent vertex that corresponds to that minimum distance that we could connect to. It is a greedy algorithm. We add the vertex with the least cost edge, and then we use a priority queue keyed on that d sub v, that distance, to find the next vertex to evaluate. It does require one of those operations in a priority queue or in a heap that we didn't use quite as often so far, and that is to be able to decrease the key. When we find a shorter route to something, we need to be able to decrease the key that's associated with it, the cost that's associated with it, and update the vertices inside of that priority queue. So here's an example. If we input this particular graph, then Prim's algorithm tells us to choose a starting vertex and to build this table. For each vertex, we'll have a Boolean to indicate whether it is known, which really means have we evaluated it? Have we popped it off of our priority queue and looked at what connections it has from there? And then this d sub v, the distance, and the p sub v, the parent that's associated with that distance. So if we start at A, for example, somewhat arbitrarily, we look at A, we mark it true as known because to know it is to look at all of the edges out of that vertex A. We've looked at all those edges and we use them to update distances and parents in our table here. So we say that B, we know it has a distance of 4 from A. And we know that D has a distance of 1 from A. And those are the minimum distances we've seen so far. They may change later down the line. So then we pop off the minimum cost edge that we've seen so far, the 1 to D, and we take a look at what's available from D. So we see that H has a distance of 5 from D, and J has a distance of 6 from D. You'll notice that H and J are not marked known yet because they have not been popped off of our priority queue to look at the edges coming out of them. So they're not fully evaluated yet, is another way to think about that. The next lowest value on our priority queue, since the 1 for D was handled, is the 4 associated with getting to B. So B will be evaluated next. From B, we see that we can connect to C, which has not been seen before and is not fully known. We also see that we could connect to J, but it's not a shorter distance than the distance that's already known to connect to J, so we don't have to change that one. We do have to update C to say that it has a distance of 4 from B. Then the 4 to connect to C is the next minimum on my priority queue. These 5 and 6 for H and J are too high. We're not going to explore them yet. We might get to them later. So we evaluate C. It then allows us to update E and F to say that they have a value of 2 and 1. That's a distance for them from C. And then we would look at the 1 from F, see that it connects to G and I, and be able to update their values. We would evaluate E because it had the distance of 2 there, and see that we actually have found a better distance to G. So you can see that first we thought we had a good deal with this distance of 3 from F to G, but in fact we had a better deal with the distance of 2 from E to G. So now that distance of 2 is our next minimum on our priority queue. That tells us that G connects to J and J and I both get their values, their distances marked as being connected to G. Even though before we had each of them connected to other nodes, they have a better cost from G, a shorter distance from G than from those other nodes we had seen. And then we explore I to see if there's any better connections there. There was to J. It's a shorter connection there. And we explore J. We see that it has a shorter connection to H than H had to D, so we update that. Then we can explore H, which is our last remaining node that we haven't evaluated yet, and we see that there's no new information to be gained from H. All of its edges have already been revealed by other node explorations here, vertex explorations. So we're done when all of the nodes are marked known. We don't have to do a search through nodes to see if they have all been marked known. We could easily just keep a count of them, so that could be a simple operation to know when we are done. And we can read those P sub V and V edge pairs to list the edges in the minimum spanning tree. We could start with A and then see who connects with A, and we could go onward through there to list those edges that would be in our minimum spanning tree. So some pseudocode for that. While our priority queue is not empty, we will pull off the minimum from that priority queue and call it U, a node, a vertex. For every vertex that's a neighbor of U, and we assume that we can quickly find, let's say we had one of those lists, the adjacency list, we could quickly find which vertices are connected to U using that adjacency list. Great. We see if that vertex is already in the minimum spanning tree. And if it is not already in the minimum spanning tree, meaning that it's not already fully known, then if the weight from U to W is less than W's current distance, then we update the parent of W to be U, and we update the weight of W to be the weight between U and W. And then if we had to update W, then we need to update W in the priority queue as well, because W was not in the minimum spanning tree, which means it has not been fully evaluated. That means it is still sitting in the priority queue, and since it's sitting in the priority queue, we need to make sure it has the correct priority. So this would require some rearrangement within the priority queue. The details of Prim's algorithm are that its running time is O of the cardinality of edges plus the cardinality of vertices times log cardinality of vertices. So it's essentially V log V, where V is the number of vertices. If we use a particular type of heap called a Fibonacci heap and an adjacency list, then we can achieve this kind of speed in it. Other types of heaps will have a little less efficient performance on some operations, like changing priorities within them once the heap has already been built. Otherwise, with our normal heaps, it's edges times log vertices. So E log V, cardinality of E, log cardinality of V. It only prioritizes edges that are connected to the spanning tree so far. It doesn't need to sort or prioritize the entire list of edges. And that means that it is optimal for dense graphs that are highly connected to each other. And as mentioned, it needs a priority queue that supports being able to decrease the key of something once it's already in there.